Chapter 9 Review. Here we go. Number 1. Consider an experiment with a null hypothesis that p is 0.76 and an alternative hypothesis that p is less than 0.76 and a possible correct value of 0.74. As our sample size, as n, increases, would that raise the probability of a type 1 error, of a type 2 error, and how would it increasing affect the power of the test? The sample size n has no effect on the probability of a type 1 error, but it does increase the power of the test, which, because that's related to the probability of a type 2 error, would decrease the probability of a type 2 error. So sample size increasing would have no effect on the probability of type 1. Doesn't matter if it goes up or down, sample size never affects probability of type 1 error. However, it increases the power of the test, and that would decrease the probability of a type 2 error. Number 2, the analysis of a random sample of 500 households in a suburb of a large city indicates that a 95% confidence interval for the mean annual family spending at Chipotle is $340 to $533. In a test of the null hypothesis that mu is equal to 400 against the alternative hypothesis that mu is not equal to 400 at the alpha equals 0.05 level of significance, could we draw a conclusion using the confidence interval? If so, what would that be? Yes, we can draw a conclusion. We would fail to reject the null hypothesis. Since 400 falls within the interval, we could not conclude that the mean annual family spending at Chipotle in this city is not $400. So just a side note here, if the interval had not included $400, then we would reject the null hypothesis, and there would be reason to suspect that the mean was something different than 400. Number 3. This is one of the more complex ones, so just try to stay with me. Mr. Struey claims that doing certain stretching exercises increases a track runner's endurance. He claims that doing these exercises every day for a month should reduce the runner's 1 mile running time by an average of 8.4 seconds. Mr. Hawkswell believes the claim is exaggerated and plans a test on an SRS of 35 runners in which they will reject Mr. Struey's claim if the reduction in the 1 mile running time is less than 6.5 seconds. Suppose the standard deviation of decreased seconds is 4.1, and if the true mean decrease is only 7.9 seconds, what is the probability that Mr. Hawkswell will fail to reject the false claim of an 8.4 second reduction? Okay, I know it's a lot of words. If you look at the very end, we want to know the probability that Mr. Hawkswell will fail to reject the false claim. So as you should know by now, failing to reject a false claim is a type 2 error. So we're really wanting to know the probability of a type 2 error. So think about this with me. If we look at our curve and the true mean is 7.9 seconds, and we're saying if it is below 6.5, if it's below that mark of 6.5, we'll reject it. Then that means this over here is the space that we will reject it. If we found that area, that would be the probability of rejecting the false claim. So that would be doing the p-value of z is less than what we have right here. Because what I just circled is how we'd find the z-score for that 6.5, because we do 6.5 minus the mean, and then divide by the sample standard deviation, because that 4.1 is the true standard deviation, and then we got to divide by the square root of our sample size, 35. But we'd be rejecting it if it was less than 6.5, so we'd be rejecting it if z was less than this number right here. So if we're wanting to know the probability of it being greater than 6.5, us failing to reject, that's why I use z is greater than 6.5 in this probability. So again, we just set up a normal p-value, and z-score, but since we're wanting to find the probability of failing to reject this area where it's greater than 6.5, we do the probability of z being greater than the boundary we're setting, 6.5, because that's what we want to be the mark, subtracting our mu right here, and then we get our standard deviation down here. Page 541 has a very similar example about potatoes if you want to look at that. It may throw you off just because they don't quite give all the numbers in that one place. You have to look at some previous examples to get some of the standard deviation numbers and things like that, but there is a similar example on page 541 if you'd like to check that out. Number 4, a medical researcher is testing the effectiveness of a new medicine. Her null hypothesis is that the new medicine has the exact same effectiveness as the old medicine. What would the result be of type 1 and type 2 errors? So type 1, a researcher concludes the new medicine has a different effectiveness than the old medicine when it actually has the same effectiveness. Type 2, researcher concludes that the new medicine has the same effect as the old medicine when in fact its effectiveness is different. So remember, type 2 is failing to reject, just like it was up in number 3, so failing to reject the false claim. Type 1 is rejecting a true claim, and type 2 is failing to reject the false claim. Number 5, when a lobby firm represents a group of people in an attempt to persuade Congress to pass a new bill, Congress does pass the bill, the lobby firm receives a percentage of the group's estimated monetary benefit from the bill. That settlement amount is based on the total number of people in the group. The larger the group and the larger the estimated benefit, the more money the lobby firm will receive. A lobby firm is trying to decide whether to represent a group of coffee shop owners who want the new bill from Congress that will decrease the tax on imported coffee. If the bill is supported by 60% of Congress members or less, the bill will not pass, and the lobby firm will not recover its expenses. Therefore, the lobby firm will handle this request only if it is convinced that the proportion of Congress willing to pass the bill is more than 60%. The lobby firm plans to take a random sample of 80 Congress members and ask them if they would be willing to pass the bill. So for part A, we need to define the parameter of interest and state the null and alternative hypotheses that the lobby firm should test. P is the proportion of Congress members who will vote for the bill. The null hypothesis would be that P is equal to 0.60. The alternative hypothesis would be that P is greater than 0.60. Part B, in the context of this situation, describe type 1 and type 2 errors, and describe the consequences of each of these for the lobby firm. So type 1, the lobby firm concludes that there are more than 60% of Congress members who will vote for the bill, so they take the case when in fact it is 60% that will vote for it. Again, that is rejecting, that is rejecting a true claim. So they'd reject the null even though the null was true. And the consequence would be that they take the request, but then they lose money. Type 2, the lobby firm concludes there are only 60% of Congress members who will vote for the bill, when in fact more than 60% would have. So here they fail to reject the false claim. And the consequence would be they return the request and they miss an opportunity to earn money. So they don't actually lose money in that case, but they do lose money they could have earned, lose the opportunity to earn money. Number 6, a manufacturer of capri pants claims that P, the proportion of its pants that shrink at least 2 inches in length after being washed 5 times, is no more than 0.03. Some customers have complained that the pants are shrinking more frequently. If the customers want to conduct an experiment to test the manufacturer's claim, what hypotheses would be appropriate? Well, the null would be the manufacturer's claim of 0.03. The alternative hypothesis would be that p is greater than 0.03 because they suspect that a greater proportion than 0.03 are shrinking. 7. In a test of the null hypothesis of mu equals 30 against the alternative hypothesis, mu is greater than 30, a sample from a normal population produces a mean of 32.4. The z-score for the sample is 1.98, and the p-value is 0.031. How would we interpret this p-value? Okay, let's go ahead and do that part. Assuming the null hypothesis is true, that mu equals 30, then there is a 3.1% chance of a sample that is 32.4 or higher. That's what our p-value means. It's the probability of something that far away or farther happening in a random sample. That would be our interpretation. So what would be the proper conclusion to make from this p-value? Since this is a very small percentage, there's only a 3.1% chance of it happening, we should reject the null hypothesis, and we'd reject believing that mu was equal to 30. It is possible that's true, but it's a very small probability of it being true, so we decide it's convincing evidence to reject it. Number 8. We'll just do that one. I've got that at the end. It's a 4-step process, so we'll do that one at the end. I probably won't come back and reread it, so just make sure if you need to pause here, just look at your own paper once we get to that. Number 9. Ed Sheeran claims the average number of top 10 hits he produces in a new album is 2. But a consumer group is skeptical of this claim, and they think that Sheeran is understating the average number of top 10 hits. So they're understating, meaning they think he produces more than just 2 top 10 hits in his albums. If mu represents the true average of top 10 hits for a new album that he produces, what would be the null and alternative hypotheses that the consumer group should test? Well, the null will be Ed Sheeran's claim that mu is equal to 2, and the alternative hypothesis would be that mu is greater than 2 because they suspect it is more than 2. 10. An AP English teacher reported the results from a reading experiment to her principal. The experiment asked, what proportion of my students actually did their summer reading assignment? The report stated that the statistical test result yielded a p-value of 0.31. How should we interpret this p-value? Let's start with that part of the question. If the teacher's null hypothesis is true, then there is a 31% probability of her sample being that far or farther away from the null hypothesis. Now, what would be the proper conclusion to make from this p-value if we are running a significance level of alpha equals 0.05? Since the p-value is greater than 0.05, we would fail to reject the null. We do not have statistically significant evidence to go against the null hypothesis. Consider a hypothesis test with the null hypothesis of mu equals 140 and the alternative hypothesis that mu is less than 140. Which of the following choices of significance level and sample size results in the greatest power of the test? When mu equals 130, would it be better to give our test greater power if we use a significance level of alpha equals 0.08 or alpha equals 0.02? And would it have greater power with the sample size being 25 or 60? The best choices, as you can see, would be alpha equals 0.08 and the sample size being 60. The reason is when significance level goes up, so does the power. So those two go together. Significance goes up, power goes up. And same with the sample size. When sample size goes up, the power goes up. So those two things go hand in hand. Significance level goes up, power goes up. Sample size goes up, power goes up. So just keep in mind, in case the question asks different things about decreasing power or something, it's really the relationships there you need to commit to your memory. make sure you know significance level goes up, power goes up. Sample size goes up, power goes up. Okay, this is answering the question about the Eggos, our lovely favorite four-step process. First, P, that's the true proportion of Eggo waffle boxes that contain the voucher for a free Thomas the Train toy. Our test will be the null hypothesis that P is equal to 0.33 versus the alternative hypothesis, what we suspect, which is that the proportion is less than 0.333. Since we're doing proportions, we will do a one-sample z-test, assuming the conditions are met. And here we look at the conditions. Random. It's fair to assume the boxes purchased were a random selection of the boxes produced. It's really hard to imagine how we could do otherwise and it just be random, so we say that's fine. Normal. The number of successes, we do the sample size times the null probability, and that is greater than or equal to 10 because it's 14. And the number of failures, n times 1 minus the null probability, we get 28, which is also greater than or equal to 10. So the normal condition is met. Independence. If we are sampling without replacement, so we need to look at the 10% condition. That should be written out there. Sorry I didn't. But it is safe to assume that 10 times 42, or 420 boxes of Eggo waffles, or many more, were made. So the 10% condition is met. Now the do. Our p hat is 12 over 42, which is 0.286. So we do our z-score. We do our p hat minus the null p over the standard deviation, and we get negative 0.646. And based on our alternative, we want to look at the p-value where the probability of z less than negative 0.646, and we get 0.259. Our conclusion. Since the p-value, 0.259, is greater than 0.05, we fail to reject the null hypothesis. Despite the great anguish it brings to our heart and the heart of our children wanting those Thomas toys, there is not enough evidence to convince us that the proportion of Eggo waffle boxes with the Thomas voucher is less than 0.333. Good luck, guys. Make sure you get the big picture concepts here. Make sure you know type 1 and type 2 errors, and you'll be great. Good luck.